We now have our third section on product operators, and first of all we're going to use these to describe a real experiment for once, the first real experiment, and then we'll have a little look at some stuff about how these multiple quantum terms arise and evolve within this theory. So the first thing we're going to look at is this INEPT experiment. This was one of the very first multiple pulse experiments, and it's become an absolutely crucial building block, particularly in heteronuclear experiments, all the sorts of experiments you might use, for example, to do protein NMR. They're all based on the ideas which arose from this INEPT experiment. So again, it's really worthwhile spending some time looking at it. Now, we have to go back in history really to understand how this experiment arose, and it basically arose because of a sensitivity problem. NMR has always suffered from low sensitivity, and you can get the greatest signal by having the largest magnetization at equilibrium. And for example, that's one of the reasons why you want to have a very high magnetic field, because that gives you a large equilibrium magnetization. And it also means that a nucleus with a higher gamma also has a higher magnetization. So proton, the gamma is bigger than carbon-13. That means the energy levels are further apart. So there's a greater population difference at equilibrium, and hence a larger equilibrium magnetization. And that equilibrium magnetization translates into a stronger signal. So the idea of INEPT is to take the large magnetization from the high gamma nucleus, for example proton, and transfer that large magnetization to the low gamma nucleus, the carbon-13, and hence enhance the sensitivity of the carbon-13 observation. So it's a transfer of magnetization from a high gamma nucleus like proton to a low gamma nucleus like carbon-13 or nitrogen-15. And we'll show that you can achieve efficient transfer of magnetization through large one-bond couplings. So the direct coupling you see between a carbon-13 and a directly attached proton, that's a large coupling. And we can do this in a way that's independent of offset. In other words, it's independent of the chemical shift of both the carbon and the proton, so it will work for all of the carbon-proton pairs in the molecule. And to do this, we're going to utilize spin echoes and coherence transfer, so all of the things that we've been putting together so far. So here is the pulse sequence for the INEPT experiment. And to start with, it kind of looks fairly complicated, but what you should now begin to do is to spot the elements of this pulse sequence, because it's actually just built up of three things. You start with a pulse to the I spin, that would typically be the proton, and then you have this tau 1, 180, tau 1, that's period A, and I hope you now recognize that that's a spin echo. So we can say exactly what's going to happen during period A. The offset will be refocused by those 180-degree pulses, and the coupling will continue to evolve. Right, we know that because the 180-degree pulses are applied to both spins, therefore the coupling will evolve. So basically what happens during the spin echo A is we will generate some antiphase magnetization due to the evolution of the coupling, but the offset will be refocused. Period B is just a couple of 90-degree pulses, and those will transfer the antiphase signal on I into an antiphase signal on S. So that's the coherence transfer step. So now the signal is on S. And then if you look at period C, it's delay 180 delay again. So this is again a spin echo. So what's going to happen during that delay is that the antiphase will go in phase, and again the offset is refocused. So this pulse sequence is just two spin echoes and a coherence transfer step. And we're going to analyze it using that idea rather than analyzing it step by step by step by step, because if you try and do that, you'll end up with pages of calculations which will be wrong. You've got to be intelligent about the way you do this. You've got to recognize what's going on. So let's do that in the cleverest way we can. And we're going to start with equilibrium magnetization on the I spin, IZ. And I'm going to put a factor Ki in front of it. Now normally I said we don't worry about this, but I want to keep track of the fact that the I spin magnetization is bigger than the original S spin magnetization because it has a higher gamma. And that's why I'm putting that Ki in. It's just a harmless numerical factor. It'll just carry forward in the calculation. We know what happens during the spin echo. We allow the coupling to evolve for a period 2 tau 1, and then we apply the 180-degree pulses, and you can very easily work out that you get an in-phase term and an anti-phase term, 2ix sz. Now we know that only this anti-phase term will be transferred. Only anti-phase terms are transferred by pulses. So that in-phase term, the IY, we're going to throw that away straight away and stop worrying about that, because that will never be transferred to the S spin. So just concentrating on the 2ix sz term, the period B consists of a 90-degree pulse about Y and then a 90-degree pulse about X, first to the I spin and then to the S spin. And if you apply those sequentially, you end up with a term in red there, 2IZSY, and that is coherence transfer to the S spin. Now, you might have spotted that the first pulse, the pulse to the I spin, is about the y-axis. And that's actually crucial, because if you apply that first pulse about the x-axis, it won't cause the coherence transfer step. So that's very important that it comes out along y. So that's what we do. And in fact, we could just stop at that point, because the signal has been transferred to the S spin, and we could observe it, and we know that what we would see would be an antiphase doublet on the S spin, and it would have been transferred from the I spin. It comes with that Ki factor, so its intensity would reflect the large equilibrium magnetization on the I spin. So it's achieved exactly what we wanted. So we could observe that, but actually we don't normally do that, because we normally want to observe the heteronuclear spectrum, the S spin spectrum, the carbon spectrum, for example, under conditions of broadband heteronuclear decoupling, because this simplifies the spectrum by collapsing all the couplings away. Unfortunately, if you're going to decouple, you can't decouple an antiphase state. Well, you can, but if you do, it just disappears. So when you think about decoupling, you think that's basically the same thing as setting the J coupling to 0. So a doublet collapses to a singlet. But if you take an antiphase doublet and collapse it, I'm afraid it just disappears completely. So as is shown there, if you decouple an in-phase doublet, you get what you want. But if you decouple an antiphase doublet, it unfortunately goes away. So decoupling is a good idea. It'll improve the sensitivity and simplify the spectrum, but we can't do it when we've got an antiphase state. So if you think back to the pulse sequence, after the 2 pulses, we've got an antiphase state. We can't observe with decoupling at that point. And that's what the purpose of the second spin echo is, which is labeled period C. That's to allow that antiphase state to go in phase. So let's have a look at that. This is the possible sequence A, where you observe directly after the transfer pulse. I could do that, but I couldn't use broadband decoupling. If I want to use broadband decoupling, I need to use sequence B, where I allow the second spin echo, I allow the signal to go in phase, and then, and only then, can I observe with broadband decoupling. And broadband decoupling is indicated by this blue rectangle here. So let's complete the analysis now. During period C, we start out with this 2IZSY term, and again the coupling evolves for the total time 2 tau 2, and we just forget about the offset. So we get this in-phase term Sx, and of course that's the term we want, because that's the term that we can observe under decoupling conditions. So how do we optimize this term Sx? Well, if we think about the sine 2 pi j tau 1 term first, to get the optimum signal we want that to be 1, and that means that 2 pi j tau 1 should be pi over 2. And of course that means that tau 1 is 1 over 4j. Again, it's a familiar thing that the total duration of the spin echo will be 1 over 2j, because that's what takes you from in phase to antiphase. So the two individual parts of the spin echo will be 1 over 4j. And if you think about the other term, the sine 2 pi j tau 2 term, that will also have to be 1 over 4j as well. So that gives us the optimum signal. So if we do that, we'll end up with ki times Sx. That's going to be the signal we'll observe. Now, what would happen if we just observed the signal directly on the S spin, just by doing a 90-degree pulse on the S spin? Well, we would then get minus Sy from the 90-degree pulse, but the size of this signal would be proportional to Ks. Right, that's the magnetization on the S spin, the equilibrium magnetization. And that will be much smaller in the case that I has got the larger gyromagnetic ratio. So I would get the advantage I wanted over just directly detecting on the S spin, because I take the magnetization from the I spin and I transfer it to the S spin. Now, in theory, this ought to work perfectly, but nothing in this world works perfectly. And you've got to bear in mind that during these delays, there will be losses due to relaxation, so that will lose some signal. And if you've got a range of values of the coupling, you can't choose the optimum value for all of the couplings. But in fact, this tends to work very well for transfer through one-bond couplings. Because one-bond couplings tend to be rather large, so the delays are short, and they tend to be cover a rather small range. So you can usually choose a good compromise value for the delays tau 1 and tau 2. So this INEPT experiment works very well for transfer through one-bond couplings in things like H to C or H to N. Now we just need to give a little bit of thought to this term that arises from the equilibrium magnetization on spin S. So you've got one term which is transferred from spin I, and you'll see that that comes out as Sx. And then you've got another term which is the direct term that came from spin S, and that comes out here as Sy. And in fact, we don't really want this latter term, because it will perturb the spectrum, it may mess the spectrum up, it may actually detract from the intensity. So we normally go through a process of suppressing this direct signal, and this is done in a very simple way using a difference experiment. So what we do is we do the experiment once in exactly the way I described it to you, and you'll find the red term, which is the one I want, the transferred term, and the black term that arises from the equilibrium magnetization of the S spin, which has just been rotated into the transverse plane and then just experiences a spin echo. And that's where that 2 pi j tau 2 term comes from. And then all you do is you repeat the experiment and you change the phase of the first pulse by 180 degrees. And what happens then is that the transferred signal, the one in red, changes sign. Why is that? Well, because if the first pulse is X, it starts out rotating onto minus y. If the first pulse is minus x, it starts out with the signal on y. And that trivial sign change just propagates forward through the whole sequence. So just by changing the sign of the first pulse, you can change the sign of the transferred magnetization. But the magnetization that arises from the S spin is not affected by that first pulse, because that first pulse is only applied to the I spin. So that's why these two terms are affected differently. And now all we do is subtract the two. And the unwanted term disappears, and the wanted term adds up. And that's a simple difference experiment. It's also an example of phase cycling. It's the first example we've come across. And we'll say a lot more about both difference experiments and phase cycling later on, particularly when we come to 2D. So this INEPT experiment, perhaps now to us it seems trivial. You know, you've just antiphase, transfer, and that's it. But it's made a huge impact when it was first described, because people realized that they could transfer magnetization through couplings. And that idea actually lies at the heart of almost all two-dimensional experiments as well. So this rather humble experiment really is a key element in more complex sequences, and we'll see that when we look at 2D. So the other topic I want to cover in this last section on product operators is about these multiple quantum operators. I mentioned that terms like I1x, I2y and so on, these are observable. We now know that these are in phase magnetization. But something like 2I1x, I2y, something with two x's or y's in it, this is not observable. And what that means is if you create this and then switch the receiver on, there's nothing there. Right? There's no detectable signal. There's a coherence in the spin system. There's some quantum mechanical state like this has been generated, but it doesn't generate any observable signal. So we want to talk about these terms a bit. Of course, there are actually also other terms that don't generate observable signals. So I1Z, right? That's not observable either. Z magnetization just sits there on the Z axis. It doesn't process. It doesn't give rise to any observable signal. And what we're looking for is a way of describing the difference between these terms. What is it that makes one of them observable and one of them not observable? And the concept of coherence order gives us a convenient way of classifying these different terms, these different coherences, and then we can then say which of them are and are not observable. So what I'm going to do first of all is talk about the classification of an operator according to its coherence order. And the formal definition of coherence order is the following. If you've got some object, some quantum mechanical state, and you rotate it about the z-axis through an angle phi, it experiences a phase shift, and that phase shift is minus p times phi. Right? So you switch the phase by phi, but the coherence experiences a phase shift of p times that. So this means that different coherence orders experience different phase shifts when you apply a phase shift to the system. And it's that that distinguishes different kinds of coherence. Now, you can already see an example which has coherence order 0, and that would be IZ. Because we've said if you take an operator IZ and you rotate it about Z, nothing happens. So that means that the phase that it acquires is 0. And that means it must have coherence order P equals 0. So IZ has coherence order 0 because it doesn't respond to a Z rotation. Now, to work out what the coherence orders of the other operators are, you have to introduce some new operators, and they're called the raising and lowering operators. And I plus is the raising operator, and it's defined as Ix plus the complex I, Iy. And I minus, which is the lowering operator, is defined as Ix minus I, Iy. And the reason for introducing these operators is that they have very simple coherence order. So I plus, it turns out, has a coherence order of +1, and I minus has a coherence order of -1, more or less by definition. And so if we take our operators, our x's and y's, and rewrite them in terms of I pluses and I minuses, we'll just be able to read off what the coherence order is. So that's why we're going to do this. So the way to do that is to realize that you can rewrite Ix and Iy in terms of I plus and I minus. So for example, if you look at this, if you add I plus to I minus, the two Ix terms add up and the two Iy terms cancel. So Ix is just equal to a half of I plus plus I minus. And likewise, Iy, you just take the difference of I plus and I minus, and then you've got to fiddle around with a complex I to get it right. But basically, the difference of them gives you Iy. And this tells you that you can express any operator in terms of I pluses and I minuses, and then you can just read off the operator what the coherence order is, because I plus has coherence order +1 and I minus has coherence order -1. Now this is all for one spin. We need to do this for 2 spins, and you do exactly what we did before. You generate all the same set of operators, but you have one set of operators for spin 1. So we have an I1 plus, which is I1x plus I1y, and we have an I1 minus, which is I1x minus I1y. And then we have the same thing for spin 2, I2 plus and I2 minus. So it's just the same definition, but applied to spin 2. And of course, in exactly the same way, if I take I1 plus plus I1 minus, it's just I1x. If I take I1 plus minus I1 minus, it's just I1y, and so on. So we can express any of our operator products we've looked at in terms of I1 plus, I1 minus, I2 plus, and I2 minus. And in that way, we can classify things according to their coherence order. So let's see some examples of how that might work. So 2I1x, I2z. Now we know what this is. This is antiphase magnetization on spin 1, and we know if we observed it, we'd see a nice antiphase doublet like this. But how does this work in this coherence order picture? Well, I1x I can write as I1 plus plus I1 minus, and I2z I don't need to do anything with at all. And I can look at this and I can say, well, the coherence order for spin 1 is +1 from the I1 plus term. It's also -1 from the I1 minus term. So in fact, it's an equal mixture of +1 and -1 on spin 1. And the coherence order on spin 2 is 0, because remember we said that Z has coherence order 0. So we can define an overall coherence order as either +1 or -1, and in fact they're present in equal amounts. So you can define a coherence order for each spin, and you can also define a complete coherence order, a total coherence order. So this term has got a coherence order of +1 or -1, and those are in fact the observable coherences. Let's do a more complicated one. 2I1x, I2x. Now, I told you that this is a multiple quantum term, and what we're now going to do is show that that is the case. So I write I1x as I1 plus plus I1 minus. And I write I2x as I2 plus plus I2 minus. So that's what that line is. And then I multiply the whole thing out, and I get 4 terms. The first term is I1 plus I2 plus. That's coherence order +1 on spin 1 and +1 on spin 2. So the total coherence order is +2. So that term is a double quantum coherence. The second term is I1 minus I2 minus. So the coherence order is -1 on spin 1 and -2 on spin 2. So the total coherence order is -2. So that's a double quantum term as well. Then we've got a term I1 plus I2 minus. So that one is coherence order +1 for spin 1, -1 for spin 2. So the overall coherence order is 0. And therefore we call that a 0 quantum term. And the other term is also 0 quantum. So we can see from this analysis that I1x, I2x is a mixture of coherence order +2 and coherence order -2. They're the first two terms in equal measure. And another two terms that have coherence order 0. So in fact, 2I1x, I2x is a mixture of double and 0 quantum. And you can only find that out using this analysis. And if you think back to our energy levels for two coupled spins, I said there were two extra transitions in there. The one from alpha alpha to beta beta, which is a double quantum transition. And that transition in this theory is represented by these I1 plus, I2 plus and things like that. And there's another transition from alpha beta to beta alpha, which I said was a 0 quantum transition. In the product operators, that's represented by terms like I1 plus and I2 minus. So that is how these terms are properly described. So I1x, I2x is a mixture of double and 0 quantum. And in fact, if you do the same calculation for I1y, I2y, and for I1x, I2y, and for I1y, all the possible ones, you'll find that they're all a mixture of double and 0 quantum. And this table shows you those. So if you look at the first line, now highlighted in red, it's a mixture of a double quantum part, the I1 plus, I2 plus, I1 minus, I2 minus, and the 0 quantum part, I1 plus, I2 minus, and I1 minus, I2 plus. Now what we're going to find fairly soon is we'll sometimes want to talk about the double quantum part only. And the trouble is that 2I1x, I2x is a mixture of double and 0 quantum. So what would I do to get the pure double quantum part of I1x, I2x? Well, if you look at this table, you can realize that if I take the sum of the first and the fourth line, which is I1x, I2x, plus 2I1y, I2y, the double quantum parts will cancel, and the 0 quantum parts will add. So the sum of the first and the fourth line is a pure 0 quantum term. So in other words, 2I1x, I2x plus 2I1y, I2y is pure 0 quantum. And equally, if I take the difference between lines 1 and 4, the double quantum part will add up and the 0 quantum part will cancel. So by taking combinations of these operators, you can generate a pure double quantum and pure 0 quantum operators. You can do the same thing with lines 2 and 3. You can do 2 plus 3 and 2 minus 3. And if you work through all the algebra, and it's a bit tedious, you can come up with the following, that there are two pure double quantum terms, 2i1x I2x minus 2i1y I2y. That's pure double quantum. And actually 2i1x I2y plus 2i1y I2x. That's also pure double quantum. And there's a conventional notation for these. We're going to call these dqx and dqy. And you'll see in a minute why we call them that. And there are also two pure zero quantum operators which are written there. So the take-home message here is that if you have multiple quantum terms, things like I1x, I2y, they're generally a mixture of double and zero quantum. If you want the pure double or the pure zero quantum part, you actually have to make these combinations. Now, how are we going to generate these multiple quantum terms? Well, you won't be surprised to find that they arise from antiphase terms. The antiphase terms do all the interesting things. So if I take a term like 2i1x I2z and apply a 90-degree pulse to that, to both spins, the I1x term is unaffected and the I2z term is rotated to I2y. And so I've generated a multiple quantum term, 2i1x I2y. That's a mixture of double and zero quantum. Notice the phase of the pulse is actually crucial, because if I change that pulse to a pulse about y, I'd get coherence transfer. And that's actually the reason why in the INEPT sequence that transfer pulse has to be about y. If you made it about x, it would end up giving you multiple quantum, which isn't what you want. So this is how you would generate these multiple quantum terms, and then we've described how you can separate them into pure double and pure zero quantum. Now the last thing is, how do these double quantum terms evolve in time? Right? Because you know how things like Ix and Iy evolve under shift, under offsets and under couplings. But we now need to look at how double quantum evolves. So the free precession Hamiltonian, the one that we've been using already, has got three terms in it: the offset of spin 1, the offset of spin 2, and the coupling term. And the slightly strange thing is that double and zero quantum states are completely unaffected by the coupling term. So if you've got double quantum between spins 1 and 2, that simply is unaffected by the coupling between spins 1 and 2. Turns out actually to be quite a useful property. So in fact, to calculate the evolution, we don't have to worry about the coupling term. We only have to worry about the offset terms. And in fact, these offset terms are relatively easy to do. So here we go. So here I've got a pure double quantum term, which is I1x I2x minus I1y I2y. And I want it to evolve under, first of all, the offset of spin 1, and then the offset of spin 2. And it all looks a bit hairy, but really it's quite straightforward. If you look at the terms highlighted in red, that's the I1x term evolving under the offset of spin 1 to give you I1x and I1y. And then you just have to do the same with all the other terms, and so you just end up with 4 terms there. And when you've done that, you can pull it all together and start rearranging it, and it looks like this, and you think, that doesn't look much better. But then you remember those very useful identities, trigonometric identities, about cosines and sines and how they're related. And if you apply that to those, this starts to simplify. You get one term which is a cosine term and one term which is a sine term. And of course, that term in red is the thing I described as dqx, and the term in y is the term that I described as dqy. So in fact, the evolution of this double quantum begins to look vaguely familiar because dqx evolves under the offset to dqy, just in the same way that ix evolves to iy, except it evolves at the double quantum frequency, omega 1 plus omega 2, which is the sum of the two offsets. So if you define omega dq as the double quantum frequency, then that evolution, which started out as a bit of a nightmare, now looks a lot simpler. In fact, it looks rather familiar. It's just the evolution of x into y. And it's absolutely, completely analogous to this evolution of ix into iy that we did right at the beginning. And you won't be surprised to find that if you take dqy and you allow that to evolve, it evolves into dqy and dqx. So in fact, this evolution of double quantum can also be represented by yet another one of these diagrams. There is dqx evolving into dqy, and the angle is omega 1 plus omega 2 times t. And you can do exactly the same thing for the zero quantum, and you'll find that zqx evolves into zqy. So in fact, although the algebra looks a little bit complicated to start with, the evolution of double and zero quantum also follows this straightforward kind of geometrical pattern. And now we've put together all of the necessary bits of our product operator treatment so that we're in a position to analyze multiple pulse sequences, particularly for two-dimensional NMR, and that's the topic that we're going to cover next.